Everyone. Everyone enjoying the conference so far? It's a really amazing program. This is kind of cool. I get to see a few conferences, and usually it's sort of, you get to see the same people over and over again. This is really good. There's so many good and new and interesting talks here, which is really cool. So I'm even enjoying it a lot. So, whoops. What was that? First up, quick question. Who's read this paper? Okay. If you remember one thing before you leave, please go read this paper. It's a really good start to it. It talks about failures in production systems and what causes them. There's lots of really good stuff in here about testing and the importance of it and how much we should do it. But one of the things this paper mentions, which doesn't cover for some very good reasons, is what is the most common cause of production outages? So the title here suggests it's all about testing. There's something else that happens in most systems that causes production outages. Anyone know what it is? Absolutely. Operational mistakes. We make mistakes with our live systems, particularly configuring them or making operational decisions. Particularly if it's 2 o'clock in the morning, you're tired, something's gone wrong, you've got to go fix the system. You'll see this a lot where a node will die, and maybe it's your primary database, and you need to go to your backup database. Twice in my career, there's been really bad cases of where we needed to sort out a machine in the middle of the night, and often people make really bad mistakes. One particular case I had where we went to go from the primary to the secondary. This is back probably 15 years ago or so. And the secondary wasn't working properly. The person working on it started to panic. They screwed up the system, and then eventually we had to go and try and get backup tapes in. This was for a live service. The backup tapes didn't work. We had no primary, we had a screwed up secondary, and we had no backup tapes. Learned a number of lessons from that. One is, try your restore procedures regularly. If you don't test your restore procedure, your backup tapes are kind of useless. But also, don't rely on people to get things right at 2 o'clock in the morning when they're tired and they're going to very easily make mistakes. What we need to be able to do is we need to be able to automate this and make decisions. Now, luckily, we're starting to get some really good, regularly available cluster software that can make these decisions at 2 o'clock in the morning when people normally would be tired and make the mistakes themselves. These algorithms are typically called cluster protocols and cluster consensus algorithms. I want to cover one of them today and sort of the challenges we have implementing that and what you kind of learn from doing it. So I'm going to start off with, what does consensus mean? One of my pet peeves about this industry is we don't look up the names of words. We don't look them up in the dictionary before we even try them. Like, we talk about random access memory. We don't want random access to memory. That would be terrible. We want arbitrary access to memory. We don't do software maintenance. It doesn't need greased and oiled. It's different. We've got lots and lots of these examples. So I like to always look up the words for things and see, are we kind of in the right sort of ballpark? Consensus, many people take it to mean having a unanimous view of something. Even the first definition in the dictionary tells us that. But usually when people are talking about consensus algorithms, consensus protocols, we're looking at what most of a group would agree is a given state. And with a consensus protocol, we want to get a majority of the group agreeing that the state of the world is in a certain way. And so what do we want consensus on? So the sort of stuff that I'm typically looking at is having logs of messages. So we've got a pile of messages, we have them in a given order, and we want to apply them to something. So there's a number of reasons why we'll be doing this. Typically, we're going to have some sort of state machine. The space that I work in, we do a lot of things in memory. So working on financial exchanges, for example, we deal with hundreds of thousands of transactions per second. We're usually working on an in-memory memory model, otherwise we can't get the performance that we need. But what if the machine crashes? How do we get the state back? We need to have it on more than one machine at a time. And for this, we apply certain protocols that allow us to replicate the state to a number of machines and have agreement that they've all reached a certain state before we progress something. We'll see this in many different ways, like actors will use some of these techniques, CQRS, command sourcing. We'll hear about immutable logs or write-ahead logs. These sort of techniques are used in lots of places, but fundamentally we need agreement on a given order of messages. There's been a number of papers and a number of work packages over the years that have looked at this. So going back to, there was a lot of work, particularly around about the end of the 1980s, when people like Barbara Liskov, Leslie Lamport, Ken Berman, and others all did a lot of simultaneous discovery around algorithms in this space. You may have heard of Paxos, viewstamp replication, atomic broadcast. These sorts of things all appeared around the same sort of time. What was an interesting challenge with all of them is they were really hard to implement, very difficult to get right. I've worked on a number of these sort of protocols over the years. It takes you a while to get familiar with the theory. It takes even longer to get them implemented and implemented correctly. It's quite a challenge to do this. A few years ago, this paper appeared, and it was talking about a new algorithm called Raft. When I read this, I thought, yes, this is the first thing I actually really like in this area, because you can reason about. They took the goal of making these things simple and easy to understand. Now, if you compare the likes of Paxos or viewstamp replication, they're very nice algorithms. They're very powerful. They actually allow more flexibility than you typically want in a real system. For example, how do you decide who has a best view of the system to decide if there's arbitration needs to occur, which state we go forward with? We elect a leader for these sorts of circumstances. In Paxos, for example, we can elect a leader that doesn't have the latest view of the world. Then we have to recover that latest view from the other nodes. With something like Raft, we can't elect a leader that doesn't have the latest view of the world. So it's a nice simplification for some of these sort of things. Now, this was a nice paper. It came out sort of 5-6 years ago. And then a few years later, this paper followed it. And this was by some people who tried to implement it and learned some lessons from it. It was an easier protocol to implement than the likes of Paxos that had come before, or viewstamp replication. Viewstamp replication has also been simplified at the same sort of time period. And I've got involved in implementing this one here a couple of times, and some really interesting lessons that come out of it. But so I'll take you through the high level of Raft and what to expect out of it to begin with. So Raft in a nutshell. We have a system that each of the nodes in the system can be in one of 3 roles, relatively simple. So you start the system up. All nodes start off in the follower role. So we have no leader at the moment. We need a leader to get agreement if we're going to progress forward. So we start up with the system, no leader. What happens at this point is we set a bunch of random timers. Whenever the first random timer goes off, one of those followers will put itself forward to become the leader by becoming a candidate. So we transition to the candidate stage at this stage. It will then request votes of the other followers. If it wins the election, it gets to be leader. So kind of nice, simple way of going forwards. We can get race conditions. We could have 2 followers go to become a candidate at the same time for leadership, get a split vote, and we end up with a failed election. We just go around and repeat the process again. And by using things like random timers, we can get away with having no central control. Lots of what we've learned in this space is all new discovery for likes of these algorithms, but it's actually not new on the sort of global scale. If you go back and you study things like multicast networks, a lot of what was done in this space now has all been done 20 years ago. So we keep finding that we get areas where people are discovering what they think is new things, but actually they were invented somewhere else before and actually used very well. A lot of the total order protocols that were done for multicast have a lot of the same things that we find in these sorts of algorithms here. As we go through these different states, what else can Raft do? Well, it's really very simple, and this is the nice thing about it being simple. We have 2 RPCs. One of them is to request votes from the other followers when you become a candidate. So the candidate will call each of the other followers requesting their vote. If they get the votes and they get sufficient votes, they can become the leader. Once they become the leader, they can start extending the log. And they do this by taking in requests from all of the clients. They apply an order to those, and then they replicate those to the followers. And they do that by calling an append entries RPC call. So 2 RPC calls, pretty simple protocol, and you send those to each of the followers. As you've sent them to the followers are responding with what they have appended to their own local log. The leader then has a view on what is the majority of the cluster's point that it's reached. Based upon that majority, that is known as the commit position, the cluster can move forward. The whole point to having this majority and consensus is if you have a failure within the cluster, can you guarantee that you can go forward still keeping the same state so customers don't see that something's missing? Well, if you work on majority, you can lose a minority of the cluster and still continue forward safely. So that's the whole point of this. So, for example, if you have 3 nodes, you can lose 1 and you can continue. If you have 5, you can lose 2 and still continue. So it works kind of nicely. Raft is an interesting protocol in that it's been well studied and it's also been well proven. So it was formally proven to have certain properties, and we get these 5 guarantees with it. We get a guarantee that only a single leader will be elected at a given time. The leader will only append to the logs. The logs will match for all of the leaders through time. The leaders are complete, and we get safety interstate machines. All just nice properties, but the thing is, it's all nicely proven. What's kind of underneath all of that? What I find quite fascinating is a lot of these things are presented, but some of the theory behind how they get to that position isn't presented, and this helps you to reason about them, especially if you start reading these papers. You read a paper and you kind of go, why? Like, first time I read the Raft paper, I noticed that there were so many paragraphs in it were incredibly ambiguous. You could actually very easily get things wrong because you would misunderstand what they're trying to say. If you have the theory behind it, you can get it right. And this is part of the challenge of implementing it. So what's important behind all of these things is basically their monotonic functions. So some of the principles of functional programming is what makes this work and what makes it quite easy to understand. I like to summarize it to people as you version all the things. Every election has a version, every message has a version. Just think, everything of any importance needs to have a version. Because once you've got a version of something, if you see an old version again later on, you know you can discard it. Like, we do this with code all of the time. We know that we have versions of everything. We should do it with everything we have in our system. And the nice thing is we can go forward with a nice immutable log, and if we see something, we see its version, we know whether we need to deal with it or we don't need to deal with it. Makes it all nice and simple. So where's Aeron fit into this? So I've been working on an open source messaging framework for the last 4 or 5 years, and it's had some nice properties. We've gone up against the fastest commercial messaging systems out there and quite convincingly beaten them in every benchmark we've dealt with. So this is all kind of cool. It's getting adopted into quite a few places. And a lot of people keep asking a number of interesting questions about its quality of service, because we talk about reliable message delivery. What exactly does reliable mean? I often get this question, is it guaranteed delivery? And sort of like putting a little trademark on this, because typically I get asked this question by one of these sorts of folks. Most organizations have sort of the architect. It's usually some person who hasn't written a line of code, maybe in a few decades. Usually they're trying to push requirements onto vendors so that they're sort of absolved from all responsibility in their own systems. And sort of saying, I want guaranteed delivery. Well, actually, having spent a lot of time in this space on both sides of the fence, you really don't want guaranteed delivery because it's not really a sensible term. Like, take it back for a second. So if I could guarantee that I can deliver you a message and you get that message taken off the messaging system, but you crash afterwards, what does that mean? It's not very useful. I like to think of it, we need guaranteed processing. We need to look at these problems end to end and take complete responsibility along the chain. Different tools can help us with this, but they can't give you any fundamental guarantees. You have to look at, well, if I get a message again, if it's going to be delivered more than once, if you've versioned it, you know how you can deal with it, and now it becomes idempotent. It's back to version all the things, and we'll be able to deal with it. So we've built a lot of this in as the sort of fundamental design. Now, there's many approaches to how we can put these things together. So let's look at how we build up something like a message coming into a Raft-based system, how does it get dealt with? How do we cope? Well, typically, we've got lots of clients. They're all sending messages into a system, usually destined for some service inside that system. If we want that service to be reliable, one of the things we have to do is make sure it's persistent, probably. We want to be able to turn things on and off again, so we're typically logging these things to disk. That's fine. That can deal with a reboot of the system, a restart that's not planned, but it doesn't deal with the machine bursting into flames. We need something else if we're going to burst into flames. So here we'll typically have more than one instance of a service. So typical way we would have found in the past is we'd have a primary and a secondary of a given system, where the primary is the one taking all of the requests in, being replicated to the secondary, and the secondary storing as well. This isn't very good from a reliability perspective. Like, what happens if one of them dies? Now we're going forward with no backup at all. What happens if the network gets split between them? Which one should be the one that's leading at that given point in time? It doesn't really help. So what we really need is 3 at least in any given system like this. So we need 3 so we can deal with things like if a network's partitioned, the side that has the majority is the only side that's allowed to go forward. And by taking these sort of approaches, we can start having a much more reliable service. Now, as we get to implement a lot of this, we put it out as open source, which is kind of cool, so all the community gets to benefit. So if you're all going to get the benefit, I think you should also share a little bit in the pain. So I'm going to share a little bit of the NIO pain of having to implement this in Java, and I'll sort of punctuate the talk a little bit with this. So kind of basically, do servers crash? Well, the whole point where we were talking about this is the fact that servers do crash, so we need to cope with that. So here's an interesting little bit of code from our code base. Now, this kind of looks a bit odd when you start to study it. It looks very weird. Like, I'm creating a file channel. I'm opening a directory, just not a file, the directory itself. I'm catching an exception that I'm deliberately ignoring. And then I'm going to call force. So like, look at the top bit of it here. Okay, opening this channel. If it doesn't get opened, it's still going to be in the null state. I get to the next bit, and if it's not null, I'm going to call force on it. So why am I doing this? Well, if you go to write a log in any sort of transaction system, you want to be guaranteed that that file is on disk and in safe storage so we can recover from it again. That's fine. We can open a file. When we write to it, we can fsync to the disk. That's now in storage. This is all good. What if you're fsyncing that file to the disk and the directory itself has not been stored yet? You end up with a file that's lost. Welcome to lost and found in a typical Unix file system. We need to also sync the directory to disk to be able to find that file again. Kind of practical thing that we have to do. Does Java have a method that lets us do that? No. We end up doing ugly tricks like this that are unsupported to make it work. There's been bugs open on this thing for a while. What we'd really like is a nice simple method to be something like this. Like, I would like to force a directory to disk and now have a reliable transaction store. But let's face it, we're now going to have Java 11. We're going to have var. Yay, we got var. Can we have save files on disk? No. What's more important? How are we getting our priorities right in this space? I'll move on. Let's look at performance. And how does this all kind of fit together? Raft, as described, is an RPC-based protocol. Now, there's some leeway to how we implement this, but let's look at an implementation that's RPC-based and what are the implications of that. So we've got a system that looks something like this. We send in a request. The request comes to our leader within the cluster. What do we need to do now? Well, we need to append it to local storage. So we've got a safe copy on this machine. We need to tell another one of the nodes, please append it to your storage, in which case it'll append it down there. Now it needs to say to the other node, please append it to your storage, and it'll append it to its storage. Notice at this stage, we're now on 3 different nodes, and we can safely recover from that. We could have actually safely recovered on 2, but we don't know which ones have it as far as the cluster goes. In this case, the consensus module can be telling this follower that the commit position is fine for you not only to store this to disk, you can actually execute it in your service. You can apply it to your state machine. And actually, while I'm at it, I can apply it to the state machine on the leader as well, because it is now safely stable in the cluster with the majority having seen that. Now think about what this means from a time perspective. Each of these calls, you call and you return, you call, you return, you block, you return. Time gets expanded quite a lot. And this time problem means that we get very much limited on our throughput, and we get limited on the response time we can have for a transaction. This doesn't really fit in very well. So what we need to do is start thinking about what can we make concurrent, what can we make parallel. Now, a lot of the papers don't talk about these sorts of things. So which bits of it can we make concurrent, which bits of it can we make parallel? In fact, a lot of people don't really understand the difference between concurrency and parallelism. I like to actually refer to a piece of work by John Gustafsson, who tried to point out that don't try to compare them directly together because they're very, very different. Like, one simple example, in a system you can have a single processor and it can be concurrent. You can time slice the work, so 2 operations can be happening concurrently, split up by time slicing. That's not parallel, because they're not actually happening at the same time. They're overlapping in time of the job, but they're not happening at exactly the same time. He pointed out quite nicely that the better way to think of these things is think about what they're the opposite of. So parallel being the opposite of serial is that, is it truly happening at the same time versus it's happening one after another? Think of concurrent as the opposite of sequential, where sequential and serial are subtly different. It's to do with time, but also order, where the sequential side brings in the order to which things happen, and this starts to become important for us in these sorts of things. Also, the vector side is also very interesting, and where a lot of our performance wins can come from is, can you do something to a batch of things at one time rather than to one thing at a time? So looking at things from the perspective of a vector versus a scalar. So where can we go for some influence on this? Say, most work has been done elsewhere before and often done really well. If you want to get really good inspiration for algorithms, look to hardware. They've been solving a lot of the problems that we try to solve in software for years before in hardware. So our CPUs are doing what's known as instruction pipelining. This is how we get performance through our CPUs. So we split up the job of processing an instruction down into its various steps and then start doing some neat things with them. So when you process an instruction in a processor, you don't just process the operation, it goes through a number of steps. First step is we've got to fetch that instruction from main memory. Then we've got to decode that instruction, because our processors typically don't work on assembly language. That's high level to them. They work on micro-ops, which are a lower level than that. So we have to convert or decode those macro-ops down into micro-ops. We then execute those micro-ops, and then at the end of that, our processors are so complex, they're doing stuff out of order. They're trying to do stuff in parallel, give it instruction level parallelism. This is part of the problem we're also now seeing with Spectre and Meltdown, because we're also speculating and running ahead. We have quite a complicated retirement phase where we're ensuring order is correct at the end of all of this. Now, if we were to go through these steps and then start the next process by doing a fetch again afterwards, this would be very slow. But if we can start to overlap these things, by the same circuitry that does the fetching starts fetching the next thing, the circuitry is doing the decoding, is decoding the next instruction, we can start compressing time. We can get greater throughput and greater reduced latency overall. So we start thinking about how we pipeline these sorts of operations. So in consensus, look at what we need to do. Well, we need to provide an ordering across things. So we need to sequence stuff. So we go through the order operation. We then need to append that log to persistent storage. We need to transmit it to other nodes in the system. We need to get agreement for the commit protocol itself. Then we need to execute that operation in our state machine. So this sort of similar sort of pipelines going on. Can we start doing the same sort of things? That way we can get much greater throughput and much greater latency. And even better, if we can batch some of these things along the way, we can deal really nicely with burst scenarios. How would that fit into here? These sort of models. Well, you could have a single thread on each node operating these things. Typically, that's what happens, but that will then greatly what we can do. If we give threads to each of the individual components in this, we can start getting a lot more concurrency and a lot more parallelism through these types of systems. So, request comes in, hits the leader. Now, if the leader can simultaneously send to all of the end users at the same time, we can get some significant wins. This sort of stuff is possible if you understand the underlying transport that you're dealing with. Then, if in parallel, we're responding back with what has been safely appended to the local storage, we can then send batch updates out again for what is the commit position, and we can start to repeat this process. Now we can pipeline through here, and we can get significantly more throughput. And this way we can sort of deal with things on a much larger scale. So, a bit more NIO pain. We have to deal with sending bytes to the network. We've got to send bytes to disk. We've got to process these bytes to understand what's inside them. So we end up dealing with byte buffers a lot, and we particularly need to copy bytes around quite a lot. So in Java, we'd typically be allocating our byte buffers, and then we'll be working with protocols and codecs that are encoding into those buffers. Like, I'm going to put in a value at a given index into that. Well, and I particularly want to do it at an index if I want to have true parallelism in my system, because if I was to use state within the buffer objects themselves, like the limit and the position, I now have a concurrency problem, which I don't want to be having. I want to do these things in parallel, so I need to not have state encapsulated inside there. State needs to belong to the user of that. So I want to put by index, not put by value. That's fine. That works really nice. Now I got to put bytes in instead. So I'm going to put an array of bytes at a given index into that, and my IDE is giving me a red squiggly line. Turns out, why is that? I can put an integer, but I can't put a byte array. I can't put a byte buffer. Seems to be a bit of a problem. So you look into it, this method isn't implemented. Well, surely somebody would have complained about this in the past. Well, yes, they did. 2004, this bug has been opened from. It still isn't closed. But we've got var. Yay! Why can we not have nice things? So, how can Aeron help in some of this? Well, again, coming back to what are some of the fundamentals of Raft. Some of the abstractions in Raft, I believe, are at the wrong level. For example, message index should be byte index. By looking at message index, we've got some interesting issues with this. We're treating all messages as equal. All messages are not equal. A 2-byte message is not the same as a 2 megabyte message in how it needs to be treated. Also, by treating it at a message index level, we're having to know that we've enveloped a message. When we look at things like appending to disk or replicating across a network, we're appending a byte stream. We're replicating a byte stream. If that byte stream is in order, we can prove through the monotonic function that it doesn't matter whether you're dealing with a message index or a byte index. In fact, you're better off dealing with the byte index. This is kind of one of the classic examples of where academia and practicality doesn't come to meet, where when you try to implement these things, some things become a bit more obvious. This is a big win for making things a lot simpler and also a lot faster and easier to reason about. How do we get things to go to many things at the same time? Well, Aeron's got some quite cool features. The fact is, it's a UDP-based protocol, so we can multicast between the nodes. We don't need to use TCP for that, so that's a nice win for sending to the other nodes. If you don't have TCP, we can simulate multiple streams as if they were multicast by using multiple UDP unicast streams, and runs on the likes of Amazon, for example, that doesn't support multicast. It's not as good as multicast, but it's a really nice midpoint between TCP and multicast as an option for doing these sorts of things. You've also got a really interesting problem, so if I'm the leader and I'm going to send data to each of the followers in the cluster, If I got to send the data, I've also got to store it myself. So I've got to store it to local disk. I've also got it to be processed in the state machine. What if the component that's writing it to disk is just observing the data stream going out to the others and dealing with it and copying it straight to disk? Especially if this is mutable. If this is an immutable log that you're dealing with, it can be viewed from many observers and they all get a view of the correct state. You don't have to do other copies. You don't have to receive the data in again. The thread doesn't have to do multiple operations. It does one operation, multiple observers, they all do their part. Great win for throughput. And we have this with our spy-based messaging where you can say, I want to spy on an outgoing stream of traffic. So I'm sending it out to the multicast result. What I can do is, rather than get this data received back in again, I just observe it on the way out and I don't have to copy it again. Another nice big win. When you've got monotonic functions applied to everything, one of the really nice properties is you can put the state of anything in a counter of just how far it's progressed. And we start dealing with things. We've got byte index rather than message index. How far have we progressed through the thing? Store that in a counter. The commit position becomes something you just consume up to. So when you go to consume the stream as a follower or the leader state machine, you just consume this up to the position that has been agreed as a commit position. You don't even have to unpack the messages, see where they start and finish. The whole enveloping side's already dealt with, so it makes it much, much simpler. And one of the big steps that most people don't realize until they start to do that, as soon as you take that step, the next big step that comes along is you can batch. Things now become a vector rather than a scalar. So if I'm going to take a bunch of bytes and I'm writing it to disk, I don't care how many messages are in there. I'm going to fill a packet or a block, and I'm going to write it to disk. I'm going to fill a packet and put it to the network. I now amortize the cost of dealing with that. What do the wins look like when we start to amortize costs? What a lot of people don't realize is batching is not at its best whenever you're batching thousands of items. Your biggest single win when you start to batch is when you go from 1 to 2. Because if you look at the amortized cost of any given operation, once you do 2 things for the same operation, each of them is now 50% of the original cost. You go to 4, you're down to 25, and you start to just see this is a curve that pays back with a very much diminishing returns. It's asymptotic as it approaches the bottom here. Your bigger wins are just all right at the start. So if you've got 2 things to send and they both fit into the same network packet, you've already got a massive win. Just starting to think around those sorts of things makes a big difference. And this applies for all sorts of stuff like system calls, network trips, disk writes, expensive calculations. Anything you do, if you start thinking about how do I amortize these costs, this is how we get much greater throughput. Like, there's a lot of discussion at the moment in the Linux kernel groups on how we do network stacks, because our current APIs, as we move up to 100 gigabit and beyond, our APIs don't let us send at those rates. We're limited by the number of system calls because there's a fixed overhead. Like, if you're looking at this from an accountancy perspective, there's fixed costs and variable costs. Our fixed costs are too high. If we cannot amortize across those fixed costs, we will be paying the penalty and being fundamentally limited. So what else do we need to think about when you build these sorts of things? And then what other interesting system or features would you build into a system that was providing a cluster with a consensus protocol on top of that? Classic one I keep seeing over and over again is timers. How do we deal with timers in these systems? So something's going to happen. I want to set a timer to go off in the future. Like, for example, I place an order into a market. If it doesn't match within 5 minutes, I'd like it canceled. I don't want it just sitting there. These sorts of systems typically running in memory. Everything has been driven off a deterministic stream of messages that are coming into it. That's the log. You cannot take state from anywhere else. Fundamentally, all state that enters the system must come in as a message. So you can't read the clock. You can't go read any other state. So how do you do timers? Typically, people pulse time in on a regular interval, but that limits the resolution we can deal with. It's better if we can make that available as a first-class function and put it into these sorts of systems. So we did this by actually thinking about it in our API. we made time a transitive dependency on the replication of the events, and now we can tie all of the events to time, which makes it nice. And so within the cluster, I can say things like, I would like to schedule a timer at a given timeout in the future. Set a correlation ID to deal with that, and the correlation ID is something you can then look up again later to decide what action you take on it. It's nice and opaque. Later on, whenever the timer expires, the deadline has passed, the correlation ID is passed back with the timestamp to this. No need to deal with time in any sort of way. One of the most fascinating problems I keep seeing happening is, what do we do with backpressure and work that's already part in progress? So you think of you're the leader of the cluster, or you're part of the state machine, and a request comes to you. You take it off whatever the input device is. So you've taken it off your socket, you've taken it off disk, whatever it happens to be. Now you go to apply it downstream, but the thing you're going to apply it to is too busy. So it applies backpressure. What do you do? Do you stop? Do you just hold this thing? Do you store the work somewhere else? Can you do anything else? You're in this really interesting, difficult state. The best thing to do is design your system so that backpressure becomes a natural thing. So if I'm going to consume from a messaging system, I'd like to be able to abort my consume whenever I realize I can't go downstream. And it's still going to be left there in the same buffer, rather than having to copy it to another buffer and copy it back again. So we do this, and here's some examples of some of the high-level code for it. Like, for example, here's a session message coming into a system. I'm going to do some simple stuff like, I'm going to look up, is there a valid session for this, and is that session, if it's not available in the system or it's in a closed state, I'm going to say, I'm going to continue over this, because I'm going to just ignore this data. If I've passed that stage and I've got a valid session that's open, I'm going to try and append it to the log. If I successfully append it to the log, I can say, okay, I'm going to continue over that instead. But if I haven't successfully appended to the log, I'm going to abort my consumption of this, so the next time I come back around again, it's still there. I can deal with it there. Nice and simple. I don't have state that I'm left, ooh, what do I do with this? I'm stuck. So thinking about these sorts of things. How do we deal with things like, how do we replay the logs? How do we deal with snapshots? Because if you're going to play a log from the start of time, you need a snapshot occasionally so you can get back and recovered in a faster way, and also get rid of some of your older logs. Often, people are dealing with distributed file systems. This becomes a complicated and a nasty beast to deal with itself. We bring them together, and the messaging system itself can record its streams. We can record these streams, and these streams can be just something we ask to replay later. Stream of bytes that you want to get again later. Makes it nice and easy. One of the final things that keeps popping up over and over again is we have multiple consumers of the same log. How do we deal with it? Well, if you're going to have the whole infrastructure tracking a service, why not track multiple services? It's just the same thing, especially if you're basing it on immutable data. Immutable data, monotonic functions, and be able to work over this is the thing that really helps. Okay, one last thing on NIOP. And we got to use byte buffer a lot. And there's map byte buffers and direct byte buffers. Now, I mentioned a number of people who contributed to the consensus protocol space. One of those people was Barbara Liskov. Many people may have heard of Barbara Liskov for something else, and that's the Liskov substitution principle, SOLID. That's what the S in SOLID stands for. Now, under the Liskov substitution principle, if you have a class, if you subclass the subclass must be substitute for the base class. It's a really nice, very simple API design. So if we have map byte buffer and direct byte buffer, and I tell you that one extends the other, which way around should it be? Where a direct byte buffer is just a byte buffer outside of the normal garbage collected heap. A map byte buffer is outside of the garbage collected heap, but it's actually mapped from a file on disk. And so it has extra features like you can force it back to disk and you can unmap it and do those sort of things. So like, who thinks that map byte buffer should be the base class and direct byte buffer should be the subclass, or the other way around? So here's two ways we could do this. Who thinks version 1 is correct? that a direct byte buffer should subclass map byte buffer? No one. Who thinks that a map byte buffer should subclass a direct byte buffer? Okay, most people in here would pass a 101 object-oriented course. Yay! What do you think the JDK actually does? So code we have out that people are copying as examples, it's just teaching the wrong things. Every time I just have to use byte buffer, it's one of the worst examples of code that's out there. I sometimes use it as a whole class in anti-patterns because there's so much goodness in there to show people. So quickly in closing, I'm running out of time here. What's the roadmap on this? Like, Aeron's been out a while. Clustering we have nearly completed for this version that's going to go open source. I expect to see it quite soon. Like, when I say fast, what do I mean by fast? Well, Aeron itself, over things like 10 gig networks with kernel bypass, can run at high tens of millions of messages per second. It can totally saturate the network. The ability to write to disk, we can run at however fast your SSD is, even whenever you're trying to f-sync it, because we deal with it all in a very friendly way. So you get the benefits when you think about how the hardware works and apply the right sort of learnings from elsewhere. We get to do some really cool things. When I first released Aeron, I showed this picture, and some people found it was quite funny. Having worked on this version of it, I think it's one of the hardest things that I've ever done. And so when you start to realize implementing cluster protocols, even when you implement ones that are relatively easy to understand, like Raft, they're incredibly easy to make mistakes with. It's very hard getting this sort of stuff right. My personal belief is anything interesting in either concurrency, distributed systems, or security, or transaction systems, if it's not done in open source, it's probably wrong. Because if there's not enough eyes looking at it, you won't see a lot of the mistakes, even in quite simple implementations. I'll kind of leave you with that thought, and thank you very much.